So we were seeing how to understand the frequency response of a system by analyzing its pole zero plot. So basically, what is a pole zero plot? A pole zero plot is something that we obtained from the transfer function of the system. So what is the transfer function? So we define the transfer function of a system as the ratio of the output Laplace transform divided by the Laplace transform of the input. So this is what we refer to as the transfer function. So this is also the Laplace transform of the impulse response for an LTI system. So let's take this transfer function. So this is mostly in the form of a rational system. So we will take an example where this transfer function is a rational quantity, meaning there is a polynomial in the numerator and there is a polynomial in the denominator. So we said that we can factorize this polynomial, which means you find the roots, and let us say that ai are the roots of the numerator polynomial. So let us say that you can write this as s minus ai. Now if bi are the roots of the denominator, then we can write this as the denominator. Now there can be a constant. Okay, so let's call this constant as some c. Now the transfer function of a system, which also we were referring to as frequency response in the case of Fourier transform, but in the case of Laplace transform we call this as a transfer function because this s can now be a complex number. It's not just the frequency, but it can also be a complex number. So general terminology is that this is a transfer function and it's given by this ratio. Okay. And this ratio is now a polynomial divided by another polynomial, and we can factorize this polynomial. The roots of the numerator polynomial are what we refer to as the zeros, and the roots of the denominator polynomial is what we refer to as the poles. And we saw that when s is equal to the pole value, then h of s, the transfer function, goes to infinity, and when s is equal to the value of the zeros, then h of s, the transfer function, goes to 0. So hence the name zeros and poles. Now we saw that just by substituting that s is equal to some j omega and finding out the distance of these frequency values from the zeros and poles, we can get to understand what would be the frequency response by looking at this transfer function and trying to find its magnitude at some s is equal to j omega. Could help us understand if this is a low pass system or a high pass system and so on. Now we can plot this in a little approximate fashion and get to understand a little more about the system. For example, we can plot what is called as this Bode plot from this. So Bode plot is basically nothing but an approximate plotting of the magnitude of the transfer function. So you compute the magnitude of the transfer function and then plot it as a function of frequency omega, where the x-axis is in the log scale. Okay. And the y-axis is in the dB scale, which means that is also in the log scale. So we plot this transfer function mod h of s, where s is equal to j omega, and we will plot it in an approximate fashion. If we do this approximation, then this is called the Bode plot, and we'll see what is the approximation that we are going to employ here. Now, so when we first take the mod or the absolute value, what would we get? Let's take the absolute value of the transfer function h of s is mod c, and you can distribute the absolute value operation inside. These are all just products. Okay. Now what happens when we substitute that s is equal to j omega? So this is still just a constant. This is independent of value of s, so that does not get affected at all. So now instead here we'll just substitute j omega and we'll just substitute j omega. And what is the magnitude of this complex number? The magnitude of this complex number is root of a square plus omega square. So let us assume that they are real numbers. So if we assume that they are real numbers, then we will get a magnitude to be of this form. So we will just simplify this as 1 plus omega square by a square, because we will just take this a outside. So if we take this a outside, then this is the magnitude for each and every factor that we have here. In other words, we can replace this with mod a root of 1 plus omega I square divided by ai square. Same fashion for the denominator as well. Mod bi root of 1 plus omega squared divided by bi squared. So we have not done any approximation so far. All we have done is just simplification. Now let's convert this to the dB scale. We have not converted it to the dB scale, right? So we'll just convert to the dB scale. How do you convert to the dB scale? Basically, you have to take 20 log mod of h of s. So the dB scale conversion, if we are applying on an amplitude or a magnitude, then you have to apply 20 log. So if it is magnitude squared, then it is 10 log. Okay. So if you're trying to find out the dB scale value of this quantity, then you have to apply 10 log, because there is already 2 here, which makes it 20 log. So if you're trying to find out the dB scale value of this quantity, which is simply the magnitude, then it is 20 log. Essentially both are same. You just have to remember when you have to use 10 log, when you have to use 20 log. Okay. This is 20 log, the magnitude of h of s. What is this? This is equal to 20 log mod c plus 20 log mod ai. So now we have m such ai minus, similarly for this bi's, we have capital N such bi's plus summation I is equal to 1 to m 20 log of 1 plus omega squared by ai squared (20 log 1 plus omega squared by bi squared). Now we can bring this power half to the front and then cancel out with 20, and we'll get just 10 here. Now this entire thing is a constant. Okay, so let us call that constant as some c dash. Okay, now what happens when omega is equal to one of these roots? Okay, so let us say that we start with omega is equal to ai. So let us say that we are trying to find out the value of this transfer function's magnitude at a frequency which is equal to one of the zeros. So as you can see, what happens is at the 0, then you can substitute here omega equals ai. At the 0, you get log of 1 plus 1, which is log of 2. So 10 log 2 is 3. So you get a 3 dB increment. So this entire term, when omega is equal to ai, evaluates to plus 3 dB. Okay. So let us say that in the Bode plot, so there is a particular value here. At this point, this is equal to, let us say, omega is equal to ai. So this point has to be whatever value that was present earlier. Let us say there was some value that was present earlier. Okay, there was this value, and compared to that value, what we would now get is something which is plus 3 dB. So this gap that we have here would be now plus 3 dB. The earlier value, the omega that was little earlier than omega equals ai, now we have gotten 3 dB more than what that was present earlier. Now what if we try to compute what happens at omega is equal to bi? If omega is equal to bi, once again 10 log 1 plus omega squared by bi square, that term is going to give 3 dB, but then we would have a minus here because this is in the denominator. Because of that minus, we would get a minus 3 dB. So, this is a 0. Now, in case we had a pole omega is equal to bi, then at that particular point, whatever is the previous value of the transfer function falls down by 3 dB. Because this was a plus 3 dB, there is an increase, whereas this is a minus 3 dB, there is a decrease. So, what this tells us is, at the zeros, there is an increment of 3 dB compared to the previous value, and at the poles, there is a decrement of 3 dB compared to the previous values. So, if we knew that there existed a 0 at this point, and let us say our transfer function looked something like this to start with, then by the time it reaches the 0, there should be an increment of 3 dB. Okay. And when it reaches the pole, there should be a decrement of that 3 dB. So, what happens to this function by the time it reaches the pole? It falls down by 3 dB. So, at the poles and zeros, the transfer function's magnitude changed by 3 dB compared to what it was before. So, this is always a plus 3 dB or minus 3 dB. So, this plus or 3, so this plus or minus 3 dB is either an increment or a decrement compared to what the value was before reaching that particular frequency. Okay. Now, what happens at the frequencies which was much before? So, we said that at the frequency values which are equal to the poles and zeros, we know that there is a change in 3 dB, but what happens much earlier compared to the poles and zeros? Let us consider the frequency values which are below the poles or zeros. Let us, for example, take a frequency value which is much smaller than the pole or 0. So, if it is much smaller, then we can say that this ratio is really small. So, compared to 1, this ratio is very small. We can say that 1 plus omega square by a square is approximately equal to just 1, but log of 1 is 0. So, for frequency values which are little away and lesser than the pole or 0, the contribution of these terms is approximately equal to 0 dB, which means that before I hit this point at omega equal to a 0 or omega equal to pole, the contribution of the 0 or the pole to the transfer function's magnitude is almost 0. It is approximately 0. So, I need not worry about what happens to the transfer function before I hit the 0 or a pole. I can just say that the contribution of the poles and the zeros to the transfer function's value is almost negligible. The only thing that is contributing is this constant c dash, and I can forget about everything else. Okay. Now, what happens away from? So, we saw what happens which is ahead of the 0 or a pole. Now, what happens after the 0 or the poles? So, after the 0 or pole, the frequency is much higher than the pole or 0. So, let us consider the case where omega is really large. So, now what happens to this ratio? If omega is really large, that is the frequency is much greater than the pole or 0 of interest, then we have this ratio omega square by ai square to be really bigger than 1. So, we will approximate this to be simply just omega square by ai square. Now, you take the log of this. Now, the log of this is now nothing but 10 log omega square by ai square. Now, if you take the log, there is a square which comes outside, so because of which you get 20 log omega minus 20 log ai. Okay. Now, this is some constant. In fact, this constant would just get cancelled out with the constant that is present inside the c dash. So that is just a constant. Now let us see what happens at a frequency which is 10 times this particular frequency. So we are considering, let us say, some omega naught which is greater than AI. Okay, and at that particular point we saw that it is 20 times log of that omega naught. Now this is a function of omega naught itself. So if you try to compute the transfer function's value away from the 0 or pole and at a frequency which is much greater than the 0 or a pole, then we see that the transfer function's magnitude is a function of the frequency itself. So because it is a function of the frequency itself, we cannot make a comment like how we did here in these two cases. In these two cases, we are exactly able to say that there was no contribution or the contribution was exactly quantified by this amount 3 dB. Now, can we quantify this in a fashion where we can make it independent of the frequency? So what we are trying to understand is, can we say by how much this transfer function's magnitude will fall down or will increase beyond the point where we hit the pole or 0. So we know that when omega naught, which is greater than, which is away from the pole or 0, we know that the transfer function is 20 log omega naught. Now let us pick another point. Let's call that point as omega dash. So that is also much greater than the pole or 0, but it is chosen such that omega dash is 10 times higher than omega naught. So why did we pick this particular value 10? That is simply because we are going to use this in the Bode plot, where the Bode plot, each division here is 10 times the previous frequency values, because we are going to plot this in the log scale, meaning the first frequency value that you will encounter is 10 raised to the power 0, which is nothing but 1 radian per second. The next one is 10 power 1 radian per second. The next two is 10 power 2 radian per second. So every box that you have here, every exponential scale. So every step increases the frequency by 10 times. So the range of frequencies that we have here is from 1 radian per second to 10 radian per second. From in this box, the range of frequencies are 10 radian per second to 100 radian per second, and the next one will have 100 radians to 1000 radians. So the frequency in the Bode plot is in the log scale, meaning it increases exponentially by 10 times from one box to another box. So for this reason, in order to understand what happens when you move from one box to another box, we'll just consider the frequency value which is 10 times greater than the point of interest. Okay. Now let's see what happens at this point. So when the frequency is 10 times the previous value, then we just simply substitute all you have to do is do the same thing, that you try to compute log of 1 plus omega square by AI square. Of course, this term is much greater than 1, so you approximate it by removing this 1 and simplify to get 20 log omega minus 20 log mod AI. So as you can clearly see, this constant term is not changing, that's remaining as such. The only thing that is changing is this term, that is W. So you have 10 times W naught. Now this can be simplified to, at least you can simplify this particular expression, this remains constant. This can be simplified to 20 log 10 plus 20 log omega naught. So what is this 20 log 10? Log 10 is 1, so it's just 20 plus 20 log omega naught, so which is the previous value. In other words, if you try to evaluate this transfer function, the magnitude of this transfer function at S equals j omega dash, then this is approximately equal to the magnitude that was present at S is equal to j W naught plus 20, and that 20 is simply coming because of 20 log 10. Log 10 is 1 because the entire log is in the base 10. So you just get an increment of 20 and that's all. So what this says is, for every increase of 10 times in the frequency, there is an increase of 20 in the value of the transfer function's magnitude, and there is a decrease if this was a pole. So, if this was a 0, then you get plus 20. So, there is a minus sign here, because of which if it was a pole, this would be minus 20. So, what it says is, when the frequency changes from omega naught to omega dash, that is 10 times its previous value, and omega naught is much greater than ai, the transfer function changes by an increment of 20. So, what we see here is that the slope is 20 now. So, this is what we refer to as 20 dB per decade fall. So, the decade here refers to a change in the frequency by 10 times, and the 20 dB refers to the change in the value of the transfer function by either plus 20 or minus 20. So, let us say we have been given some transfer function and we know its poles and zeros. So, for example, let us say there is a 0 here, there is a pole here, another pole here, and another 0 here. So, let us say this is how the poles and zeros of a given transfer function looks like. Okay. So, which means there is a quadratic polynomial in the numerator and a quadratic polynomial in the denominator. Now, let us plot the frequency values. So, the frequency here is 10 power 0, 10 power 1, 10 power 2, 10 power 3, 10 power 4, 10 power 5, 10 power 6. This is radians per second, and here we are plotting the magnitude of Hs, and this is in the dB scale. Okay. So, what is the magnitude? So, the magnitude that we are plotting here, that is the 20 log of the transfer function, is equal to some constant c dash plus some contribution due to zeros. So, let us call that some xi minus some contribution due to the poles yi. Now, the first 0 exists at this particular point. Okay. Now, when we are considering frequencies which are far away, lesser than the poles and zeros, we know that there is no contribution due to them. So, because of which we will start at 0 dB. Okay. So, technically these two terms are contributing to no value in the transfer function's magnitude. So, we should ideally start at c dash. Okay. But in most cases, when you are plotting this, we will start with 0, which is as good as normalizing this transfer function. Okay. So, we will normalize with the transfer function's value, which is the value at the omega equal to 0, which is basically the DC frequency response. So, we will normalize this to start at 0. It is not necessary that you should do that, but this is just a convention, but ideally we should be starting at c dash. Okay. We will normalize and say we will start at 0. So, because we are considering frequencies now which are much smaller than the poles and zeros, we will just say that this is almost a straight line, nothing is changing because the contribution of these terms is 0, and these are the only two terms that are function of frequency. C dash is not a function of frequency. So, the transfer function's magnitude remains constant till we hit a pole or a 0, and when we hit a pole or a 0, there is a change by 3 dB. So, by the time that we hit this point, we should see a change in the magnitude. So, let us say this is our point. So, there should be a change of 3 dB. So, we can just interpolate our function smoothly so that this difference that we have here is 3 dB. All right. So now we have plotted the Bode plot till the first 0. Now let's consider the region which is here, which is after the first 0. So after the first 0, so we are in the range of frequencies for which the frequency is greater than the first 0. So we have to apply this rule while plotting for the magnitude of the transfer function in this region. Okay, so the effect of this particular 0 is now going to cause an increase of the transfer function's magnitude by 20 dB per decade, meaning what we have to do is we have to keep increasing this transfer function's magnitude such that, so this is, let us say, a 10 times increase in the frequency value, then this is 20 dB. So then the y-axis intercept should be 20 dB. So this should be 20 dB. So you have to plot such that the slope is now 20 dB. For every 10 times increase in the frequency value, there should be a 20 plus 20 increase in the y-axis value, that is the magnitudes plot, the transfer function's magnitudes plot. So this is how the function increases, and the contribution of the poles that are present here, here and here are still 0 because those frequency values that we have plotted here are still below these poles and the last 0. So their contribution is still 0 dB according to this rule because those frequency values are much smaller. Okay. And now what happens when we are approaching this frequency value? So when we are approaching this frequency value, according to this rule, we have to see a minus 3 dB fall. So as the transfer function increases here, it starts falling down. In other words, this will cancel the plus 20 dB that we had earlier. So from here on, there is a flattening out because what happens, we had a 0 earlier, and in these frequency ranges, which is now away from both the 0 and the pole, we have a plus 20 dB because of the 0 for all these frequency ranges. And from this frequency range, we have a minus 20 dB because of the pole that is present here. Okay. So because of this reason, now we have a Bode plot which is going to now be a flat straight line. That is because these two 20 and minus 20 cancel out each other. Now once again we have a straight line which is now going to decrease by 3 dB when we hit the next pole, and after that there is a minus 20 dB again because of the next pole. From here on there is a fall again, okay, till we hit the next 0. So the moment we hit the next 0, what happens? It flattens out because we have a plus 20 here. So this is what we do in a Bode plot. So in a Bode plot, typically what happens is even this 3 dB fall is or rise is ignored, and only this minus 20 plus 20 is plotted. So we get a very approximate transfer function or the frequency response of the system. So this entire system now can be approximately plotted as a straight line till you hit the first 0, and when you hit a 0, just increment the slope of your transfer function by plus 20 dB per decade. So just keep drawing a straight line which has a slope of plus 20 dB per decade till you hit another pole or a 0. So now you have hit a pole, which means you have to reduce minus 20. Now from there draw a straight line because there is a plus 20 because of the 0 and minus 20 because of this pole. So effectively cancelling out, and draw a straight line. Now you saw another pole. So this plus 20, minus 20, minus 20. Now you have effectively minus 20. So you start drawing it in the negative direction. The slope is negative. Now you have hit a 0. So plus 20, minus 20, minus 20, plus 20. Effectively it is 0 again. So it's a straight line. So the Bode plot in the most approximate manner is drawn like this, where you just increment a plus 20 wherever you see 0, and you just decrement a 20 dB wherever you see a pole. So this is a very approximate plot for the frequency response of a system, which can be obtained through the magnitude of the transfer function, which is obtained through Laplace transform. The actual frequency response would be a smooth function which probably goes somewhat like this. But this can be obtained by evaluating the exact magnitude of the transfer function, but most practical applications we don't need really the exact value, we just need to know what happens in some frequency band, that's all. So for this reason, for an approximate understanding, we use this Bode plot, and all we do is just say that we'll increment or decrement by 20 dB per decade, and we know that at the point of a 0 or a pole, actually there is a 3 dB fall. So this is what typically we call as a 3 dB cutoff regions, where there is a fall in the response of the system compared to the frequency values which are much away and lesser than the pole or a 0. So for a practitioner, if you want to understand how a system responds to a certain set of frequencies, if you want to understand the frequency response of the system, all you have to do is find its Laplace transform, find the impulse response, find the Laplace transform of the impulse response, and if it's in the form of a ratio, all you have to do is compute the poles and zeros and you're done. So if you know the poles and zeros, then you can start plotting this just using this rule. All you have to do is increment by plus 20 or minus 20, depending upon if it is a 0 or a pole, and then you have an approximate representation of its frequency response. From this you can understand if this is a low pass filter, or this is a high pass filter, or this is a band pass filter or a band reject filter. All these things can be understood just by looking at the Bode plot, and in fact from this Bode plot you can see that this looks like a band pass filter, right? So for a band of frequencies it has a higher gain, and for other bands it has a very low gain. So this is like a band pass filter. So depending upon the pole 0 locations, we can clearly say that okay, this is this kind of filter and so on. Now let us say I want to increase the gain in this band pass region. What should I do? Now this is a design question. So if you want to answer the design question, clearly what it says is I have to increase the gain, which means the slope of this transfer function has to increase. So if the slope has to increase by, let us say, another 20 dB per decade, I want a higher slope here. So what should you do? Which means that you may want to have a 0 somewhere here, right? If you add a 0 somewhere here, then the slope increases even more. So this tells you what to do, how to construct a filter where you should have a pole or a 0 such that you would get the frequency response that you desire. Now if I say that I should have a frequency response something like this, then clearly just by knowing what your requirement is, it is also telling you where you should have a pole or a 0. So there should be a pole here and there should be a 0 here. So just by knowing your requirement, you will know what should be the pole 0 locations, and once you know the pole 0 location, you can construct this transfer function back from that. So once you construct a transfer function back from that, you will know what would be the impulse response. All you have to do now is try and construct a system, try and find what should be the resistor values, capacitor values, and what should be the inductor values, such that you get a pole and a 0 in these locations. So that would be the design problem that we can solve.